So there are trends within some of these families. We're going to look at the alkali metals, the halogens, and the noble gases. So looking at the alkali metals, as we go down the column, we've talked about atomic radius. The atomic radius increases as we go down. They get larger. Increasing would be ionization energy and electron affinity. Density, reactivity, and melting point we haven't talked about specifically, but there are trends in those as well. The alkali metals have very low ionization energies. They are easy to ionize. So they make good reducing agents because they're easy to oxidize. Oxidation is loss of electrons. These are oxidized easily. They make great reducing agents. They're very reactive. They are very reactive because of their low ionization energies. When they react, they lose an electron, and because it doesn't take much energy to do that, they react very easily. In fact, we don't find them as elements in nature. They're always combined with something. So the alkali metals undergo some classic reactions. They're going to react vigorously with nonmetals, such as the halogens. When they do that, you're going to get a metal halide. And we can predict the formula because of the charges for the ions. Alkali metals always form +1 ions. Halogens always form -1 ions. And so whatever the metal is and whatever the halogen is, it'll be 1-to-1. Alkali metals react explosively with water. Here we've got pictures of lithium, sodium, and potassium. There are also trends in the halogens as we go down. Again, we see atomic radius and ionization energy changing. The radius is getting larger. The ionization energy is decreasing. The halogens have very high electron affinities, and so they will gain electrons easily. That's reduction. Makes them good oxidizing agents. They're also very reactive and not found uncombined in nature. They form compounds that are generally soluble in water. Reactions of halogens, they'll react with metals to form metal halides. So we saw the alkali metals reacting with halogens. Here, this metal could be any different kind of metal, any kind of metal. And so the stoichiometry here will depend on what charge the metal ion takes. They will react with hydrogen to form hydrogen halides, HX like HCl. So HCl is a pure molecular compound, is a gas at room temperature. If you dissolve that in water, then it's called hydrochloric acid. So we can write balanced chemical equations for each of these types of reactions. And this tends to freak students out a little bit because they're like, oh, wait a minute, how am I supposed to know how to do this? The first one, if you just don't freak out about it, isn't too bad at all. A reaction between aluminum metal and chlorine gas. Well, the first thing is to write down the formulas for the reactants, right? So we've got aluminum. What's the state of aluminum? Solid. So aluminum metal and chlorine gas. What's the formula for chlorine? Cl2. It's one of the 7 diatomic elements. Cl2, that's a gas. And now we need to predict the product, the formula for the compound that forms between aluminum and chlorine. We learned how to do this in chapter 3. What kind of an ion does aluminum make? 3+. So Al3+. And what kind of an ion does chlorine make? -1, right? So we're going to need 3 of the chlorides to balance the charge on the aluminum. So it's going to be AlCl3. Ionic compounds have high melting points. They'll be solids at room temperature. This isn't aqueous because this is not happening in water. This is just two elements reacting. Then we need to balance the equation, right? Aluminum and aluminum, that's fine. But here I've got 3 chlorines, and there I've got 2 chlorines. So I could use a fraction, but I don't want to do that. This is an odd-even issue. If I double the odd thing, it becomes even. Of course, then I have to take care of the aluminum because I messed that up. Now I've got 6 chlorines, and so if I put a 3 in front of that, I can balance it. Let's write an equation for the reaction between lithium metal and liquid water. So we saw that happening over there, right? So lithium metal, it's a solid at room temperature, and water, H2O, liquid, right? What do? Well, lithium is going to form a compound, it's going to form an ionic compound, right? What kind of an ion is lithium? What's the charge? +1. So I've got Li plus, and then we have to figure out what to do with the hydrogen and the oxygen. What color did that solution turn when the lithium reacted with water? Pink. Because phenolphthalein is pink in an acid or in a base? In a base. So that solution must be basic, right? There's hydroxide ions. So we're forming lithium hydroxide. That's the formula for lithium hydroxide. Is that soluble in water? Yeah, because all lithium compounds are soluble in water. And this one is happening in water, so this would be aqueous. And then, what's the other product? Hydrogen gas. So the lithium didn't ignite, but the potassium did, right? The flames, that was from the hydrogen gas getting hot enough that it ignited. So then we got to look at this and say, well, how are we going to balance this? We've got 1 oxygen and 1 oxygen, 1 lithium, 2 hydrogens and 3 hydrogens. Well, if I put a 2 here, then I've got 2 and 2, 4 hydrogens, right? And so then I could put a 2 over here in front of the water and get 4 hydrogens. And that gave me 2 oxygens, but I also had 2 oxygens over here, 2 lithiums, and so I need to put a 2 over there. That was definitely trickier. Any questions?
So what was the reasoning we put OH?
Well, we know that alkali metals react with water to form alkali hydroxides. And over there in the hood, we reacted 3 different alkali metals, and I had phenolphthalein in the water, and so it turned pink because in the course of that reaction, it's generating hydroxide ions. So it's something you kind of just have to remember. The only other really possible combination that you could come up with would maybe be lithium oxide, because it's got to form an ionic compound with something, and you've only got hydrogen and oxygen there. Gaseous hydrogen and liquid bromine. What's the formula for hydrogen? H2. So that's a gas. And what's the formula for bromine? Br2. Those 7 diatomic elements, right? And that's a liquid. So how do we figure out what this formula is? Have we seen compounds like H and Br before? We saw HBr aqueous, right? And that was hydrobromic acid. And what ions does that form in the water? It forms hydrogen ion and bromide ion. HBr is a molecular compound, but we can use the ion charges to predict its formula. So this is going to make HBr. And this is not happening in water. I wouldn't necessarily expect you to remember this, but that would be a gas. Pardon me? I don't know if that one has a color. Well, bromine is definitely a dark brownish purpley color. I don't know about HBr. To balance it, we need to put a 2 there. When doing a problem like this, don't just throw your hands up and say, I don't know. Try to figure it out. You probably know more than you think you do. And if you just pull together the pieces that you do know, you might be able to figure it out. There's also trends in the noble gases, again with the ionization energy increases going down. Ionization energy decreases going down, atomic radius increases going down. Those ionization energies are really, really high. Noble gases are exceptionally unreactive. In fact, before the 1960s, there were no known compounds containing noble gases. People thought they just didn't react at all.